Yeah, I forgot the recording is starting now. So just go through this section once more. So these are the important formulae also that we had seen the derivation of in the last lecture, but now the application is going to be more important than the derivation. So okay, so this was this part of it. Now the next part of it is once we have this kinetic interpretation of temperature, and from this the ideal gas equation. Now we can see that RMS speed can be related with temperature now, and therefore this becomes 3 RT by capital M or 3 KT by small m, where of course R we know is the universal gas constant. And K is R upon Avogadro's number, and this is called the Boltzmann constant. Okay. So substituting this now, we also see that the average translational kinetic energy per gas molecule, that is half mv RMS square, becomes 3 by 2 kT. So this also becomes an important relation for us. So for example, if we have two samples of gas, in chamber A, for example, we have oxygen gas at 27 degrees C, and in chamber B, we have, let's say, helium gas at let's say 127 degrees C. We want to find ratio of RMS speed of gas molecules in A is to B, and then we want to find the ratio of average kinetic energy of translation for gas molecules in A is to B. And we can see that we can relate these formulae over here. Yes, Jenny, we will discuss some of the HC Verma homework problems towards the second half of the lecture. We'll discuss today because I will just complete this portion of kinetic theory of gases, and then instead of going on to first law of thermodynamics, we'll discuss some questions and doubts and things only because we have the test coming up on Sunday. Okay, so anybody got the answer for this question? So it's pretty easy. You can see that in chamber A, okay, your temperature is 300 Kelvin and the molecular mass is of oxygen. So it is 32 grams or 32 into 10 raised power minus 3 kg. Whereas in your chamber B, the temperature absolute value is 400 Kelvin and the molecular mass for the gas is molecular mass of helium, which is 4 grams or 4 into 10 raised power minus 3. So using the formula of VRMS first, this is the appropriate formula because we don't know the volume and pressure, but rather we know the temperature and molecular masses. So we can see that the ratio of RMS velocity in A is to B will just become square root of TA by TB into MB by MA, right? Just substitute this. So this is 3 by 4 into 4 by 32. So that is square root of 3 by 32. Yes, that's correct, Aman. So VA is to VB for RMS speed will be square root of 3 is to square root of 32. You can just leave it this way only, the answer. So it's just a very simple conceptual thing that, when you are comparing RMS speed of two gases, the important thing is the temperatures and the molecular mass or the molar mass, whatever. Whereas when you are looking at translational kinetic energy, average translational kinetic energy per molecule, basically you're looking at half mv RMS square. So that is just 3 by 2 kT. So here, then it depends only on the temperatures. Okay. So half mVA square is to half MAVA square is to half MBVB square. This quantity will just be the ratio of TA is to T. So that's just 3 is to 4. So these are just some basic things about application of kinetic theory of gases. It should be 100% clear to you. Okay, now next up, we look at a very interesting further application of kinetic theory of gases concept, and that is the equipartition of energy. And the principle of degrees of freedom for an ideal gas. So we have already seen that half mv RMS square is 3 by 2 kT for any ideal gas. Okay. And we also know that V RMS square is Vx squares average plus Vy squares average plus Vz squares average, and Vx squares average is equal to Vy squares average is equal to Vz squares average, which is equal to V RMS square by 3 from the concept of Brownian motion. Whereas this here, as you can see, is the definition of RMS velocity. So from these two together, you can see that half m Vx squares average is equal to half m Vy squares average is equal to half m Vz squares average, which is 1 by 2 kT. So each of these quantities, they are called translational kinetic energy, or they are average translational kinetic energy per degree of freedom. Okay. Now, where does this term degree of freedom come from? It comes from the idea that for translational motion in 3 dimensions, instantaneous velocity is the sum of components in 3 mutually perpendicular directions or along 3 mutually perpendicular axes. So we say that velocity vector has 3 degrees of freedom in the case of 3-dimensional motion. Each degree of freedom being mutually perpendicular axis for components. Okay. Now, this statement that we have written earlier, this now implies that translational kinetic energy on average, that is half mv RMS square, is equally partitioned or equally distributed among the 3 translational degrees of freedom. And that is basically part of the law of equipartition of energy. That is part of the concept of equipartition of energy. That because the average translational kinetic energy per molecule is 3 by 2 kT, and because we know that from statistical averaging and Brownian motion, V RMS square is equal to 3 times Vx average, Vx squares average, or 3 times Vy squares average, or 3 times Vz squares average. So we know that half m V RMS square is equally partitioned among the 3 translational degrees of freedom, or among the 3 terms, half m Vx square and half m Vy square and Vz square on an average. So this is like one of the inferences of the equipartition of kinetic energy in an ideal gas. Now this inference is going to go further, one step further also, but first just note down this part. Yes, Nikita, to answer your question, no. First law of thermodynamics will not be coming on Sunday's test because we will cover it only next week. Okay. On Sunday's test, it will only be up to kinetic theory of gases, but including the concept of equipartition of energy that we are learning today. Okay. So most of it is like based on last week's lecture, but with the additional concept of equipartition of energy that we are learning today. Okay. It's a small little concept, but it's important part of kinetic theory of gases. So this is going to be there. Okay. Now the thing is, what we'll understand next is depending on shape and structure of the different gas molecules, it can also store not only kinetic energy for translation, but also kinetic energy for rotation and vibration. And therefore, the total degrees of freedom for kinetic energy increases. Translational kinetic energy, of course, will have only 3 degrees of freedom. So all gas molecules have 3 translational degrees of freedom. Okay, because in any situation, a gas molecule is translating in 3-dimensional space. Because all gas molecules translate in 3D space. You're never going to have a situation where a set of gas molecules is translating only in a 2-dimensional plane or only along a 1-dimensional axis. That's never going to happen. They're always going to translate in general 3-dimensional space. But in addition to this, depending on the shape and structure, gas molecules can also rotate and/or vibrate with multiple degrees of freedom. For example, let's take the case of diatomic gas molecules. Like oxygen, hydrogen, nitrogen, any of these. Okay. Now the shape of such molecules, diatomic gas molecules, they are linear in shape, or they are what we call dumbbell shift. Okay, so imagine just 2 atoms joined together by a bond. So L is the bond length. So if we take the axis of the molecule as our x-axis, axis along which the bond length exists, and the 2 other mutually perpendicular axes passing through the center of mass as the y and the z axis, we can see that the moment of inertia about the x-axis is 0. Okay, that will be 0 because both the particles or atoms lie on it. So it's like 2 point masses lying along the x-axis. Okay. So the atoms are treated like point masses or particles, but moment of inertia about y-axis is non-zero. Moment of inertia about z-axis is non-zero. In fact, Iy will be equal to Iz, is equal to Iz. So such a molecule in general, so a diatomic molecule in general has a kinetic energy of translational kinetic energy plus rotational kinetic energy. Its total kinetic energy is the sum of translational plus rotational kinetic energy. Now we can see here that okay, so half m d RMS square is this quantity, but half I omega square because moment of inertia about the x-axis is 0. So we can see that along with the 3 translational degrees of freedom, diatomic molecules have 2 rotational degrees of freedom. So they have 3 translational plus 2 rotational degrees of freedom. Yes, Nikita, Ix is 0 because both our point masses are lying on the x-axis. So the radius of gyration will be 0. So remember, for discrete particle system, our moment of inertia is summation mr square. So both the particles are lying on the x-axis. Ix will be 0 because both point masses or atoms are on the x-axis. So about the x-axis, the system has no radius of gyration. Whereas if the bond length is L, then each of those atoms has a radius of gyration of L by 2 with respect to the y-axis or with respect to the z-axis. So from the center of mass of the axis of the atom, you can see that there are 3 mutually perpendicular axes possible, but one of them, the distribution of mass is such that moment of inertia is 0, and the other two, the distribution of mass is identical and moment of inertia comes according. Yeah, moment of inertia. Yeah, moment of inertia is a scalar quantity. So no, Aman, moment of inertia does not have sign. It is a modulus quantity. It is summation mr square or integration r square dv. And in any case, perpendicular axis theorem, what you're referring to, it applies to laminar objects. Iz is equal to ix plus iy, where z-axis should be perpendicular to the laminar or the plane of the body, and ix and iy should be about axis lying in the plane or in the laminar. So to a linear object, we cannot apply perpendicular axis theorem. You can apply parallel axis theorem, but that's not necessary over here. You can see the symmetry. Omega is angular speed, beta. Rotational kinetic energy. So here we are talking about, for example, if this dumbbell shaped particle or dumbbell shaped molecule is rotating about the y-axis with angular velocity omega y about the y-axis, then its rotational kinetic energy will be half iy omega y square. If it is rotating about the z-axis, which is this one, so it's rotating like this. So its kinetic energy of rotation will be this. We've done basics of rotational mechanics, no? So you know that rotational kinetic energy is given by the term half I omega square, where omega is angular speed and I is moment of inertia. Yeah, radius of gyration for a particle is its perpendicular distance from the axis of rotation. If a single particle is at a distance, perpendicular distance r from the axis of rotation, so it's describing a circular path of radius r, then that particle's radius of gyration becomes r. Of course, for a rigid body, then we define the radius of gyration in such a way that if moment of inertia is I, it is mass of that rigid body into radius of gyration squared. So, for example, if you have a rod which is rotating about one end, mass m and length l, you know that the moment of inertia is ml square by 3. So, the radius of gyration is l by root 3. that's for a rigid bond. If you're talking about a single particle, then the radius of gyration is nothing but the perpendicular distance from the axis of rotation. So it's like part of the fundamentals of the concept of moment of inertia in rotation, the concept of radius of gyration. Anyway, so hope this point was clear, na? Vaishnavi? Okay, so now coming back to what is important for us over here, and that is the application of the law of equipartition of energy. So now what the law of equipartition of energy says, in thermodynamics or in kinetic theory of gases, it says that all degrees of freedom will have equal partitioning of kinetic energy. So it says that the average kinetic energy per molecule per degree of freedom is equal to 1 by 2 kT. So therefore, for a diatomic molecule, half m Vx squares average is equal to half m Vy squares average is equal to half m Vz squares average is equal to half Iy omega y squares average is equal to half Iz omega z squares average is equal to 1 by 2. Okay. And therefore, half m Vrms square will become 3 by 2 kT because the degrees of freedom are 3 for translation. But half I omega squares average will become kT because degrees of freedom are 2 for rotation of diatomic molecules. And therefore, average kinetic energy per molecule, which is this thing, that becomes 5.2 kT because the translational kinetic energy has 3 degrees of freedom and the rotational kinetic energy has 2 degrees of freedom. So total degrees of freedom is 5. So that is 3 translational plus 2 rotational. Degrees of freedom. So from this, what we remember that diatomic molecules have total degrees of freedom equal to 5. We just refer to it as degrees of freedom. There is one exceptional case I will discuss about diatomic molecules also, but in general, the default value of degrees of freedom we take for diatomic molecules is always 5. Okay, so the concept of equipartition energy is this, that whether it is rotational kinetic energy or translational kinetic energy, each degree of freedom has equal partition of energy. So the average kinetic energy per molecule per degree of freedom is always equal to half kT in any type of gas molecule, irrespective of how many total degrees of freedom it has, and irrespective of the types of kinetic energy it stores. So the two standard examples, now before I forget, for diatomic gases at extreme temperatures, there might be vibration of the molecule with respect to its own bond length, but that is only at extremely high temperatures. So this type of vibration might also occur. So in this case, the total degrees of freedom becomes 3 translational plus 2 rotational plus 1 vibration. So that becomes 6. So in this case, at extremely high temperatures, when vibration is occurring, the average kinetic energy per molecule will become 6 times half K. But this is an extreme situation. In general, for diatomic molecules, we take the degrees of freedom as 5, and so we take the average kinetic energy per molecule to be 5 by 2. Okay. So the standard value of degrees of freedom you should remember for diatomic gases should be 5. Now the second standard thing we should know is for monoatomic gases, which is even simpler. Or what are called the noble gases, helium, neon, etc. The molecule is a point mass, so it has no rotation possible. I mean, there is no moment of inertia about its own axis, so only translation is possible. So moment of inertia is 0. So the kinetic energy is only half m v square. It's pure translational kinetic energy. So degrees of freedom is 3. So average kinetic energy per molecule is 3 by 2 K. So standard value for diatomic molecules is 5 by 2 kT, and for monoatomic molecules it's 3 by 2 kT. Okay, so now from this, the last important concept here is that if we have polyatomic gas molecules, like ammonia gas or sulfur dioxide or carbon dioxide, etc., methane gas, then degrees of freedom can be 5, 6, 7, depending on shape and structure. Because obviously F will be 3 for translation, but can be 2 or 3 for rotation. Okay. 2 in the case of a linear molecule. Example, carbon dioxide. But 3 in the case of more complex molecular shape, 3-dimensional kind of shape. Like for example, methane gas, tetrahedral. So they are almost like rigid bodies, the molecules. And can be 1 or 2 for vibration, because depending on the structure, the molecule can have vibration of its atoms along different axes. So end of the day, basically for polyatomic gas molecules, is unpredictable. The value of total degrees of freedom cannot be fixed at a certain number. Depends on the particular gas in concern. And the temperature range also, because vibration tends to occur more at high temperatures. Okay, so at our physics level, we don't need to really bother about these things. We'll mostly be dealing with monoatomic and diatomic gas molecules, for which you will use the standard values of degrees of freedom of 3 and 5. And in case of polyatomic gas molecules arising in any question, the question will give you the value of degrees of freedom that you could take. But as you know, in chemistry, in your thermodynamics, you look at degrees of freedom in more detail. You might be looking at degrees of freedom for several particular structures for gas molecules. Okay, so hope this concept is clear to all of you. Now let's quickly look at an application example using this. So first of all, if we have a sample of gas which is of n number of moles, n moles of an ideal gas which has degrees of freedom equal to F at pressure T, volume T, and temperature T. If we know that half mVRMS square is 3 by 2K, because whatever be the total degrees of freedom, translational degrees of freedom are only 3. Okay, we know that average kinetic energy per molecule per degree of freedom, that is half K. So the average kinetic energy per molecule, that becomes F by 2 K. So now the total gas, the total kinetic energy of the gas molecules in the gas sample, this is what we refer to as the internal energy of the gas. And we give it the symbol U. Because if you recall from assumptions of kinetic model, gas molecules do not have any intermolecular attractive force. Okay, so therefore, now potential energy. So the only type of energy that is stored is kinetic energy. So that is why the internal energy of an ideal gas, it is pure kinetic energy of molecules. There's no other form of energy that a gas internally stores. Okay. So now we develop a formula for this internal energy of the ideal gas, which is the total kinetic energy of its molecules. So that is equal to nothing but number of molecules into average kinetic energy per molecule. So that is n into Avogadro's number of moles into Avogadro's number into F by 2. Okay. Now we recall that Avogadro's number into K is nothing but universal gas constant. So we get the very important relation that the internal energy of an ideal gas is given by the formula NF by 2 RT. So when we pick up first law of thermodynamics, the next chapter in the following week, you see this is going to be a very important formula for us. So it's important not only from this chapter, kinetic theory of gases point of view, but it is like a fundamental building block of thermodynamics and first law of thermodynamics application. That the internal energy of an ideal gas is given by this relation, and it is nothing but the total kinetic energy of the gas molecules, where F is the total number of degrees of freedom. Yeah, just give me some time to note down all this. Yes, Amog, you wanted to go through this part, the polyatomic gas molecules, or no? Okay, so now let's come to this part below. So internal energy of a gas sample, that is explained over here with the formula. And keep in mind that the standard values are that F is equal to 3 for a monoatomic gas and F is equal to 5 for a diatomic gas. F always stands for the total number of degrees of freedom, unless we specify that we are talking about translational degrees of freedom or rotational degrees of freedom only. Yeah, so let us now start looking at applications of this concept. So we have a gas chamber which has oxygen total internal energy of the gas molecules. Okay, so these three things we have to calculate. We'll take R as 8.3, or let's take 8.31 joules per mole Kelvin. And let's take 1 atmosphere as approximately 10 raised power 5 pascals. So you can see this type of question is extremely formula based. There's nothing more to it. PRMS standard formula. So oxygen gas and it's diatomic. Degrees of freedom will become 5. This will be in meters per second. We'll calculate it in a moment, but I'm just showing you what all formulae you need to use. Then average kinetic energy per molecule will be 5 by 2 kV. It's becoming joules. And total internal energy will be so this is the easiest of the lot. Because the pressure is 2 atmospheres and the volume is 10 liters. So it's 500 joules. So the total internal energy is 500 joules. So hope this calculation is clear to all of you. Okay, so with this we finish the important part of kinetic theory of gases, and we'll be ready to move on to first law of thermodynamics in the next session. So now we can discuss if you have any doubts from your homework questions or any exercise problems so far. We can first discuss those. Javal, I think you have sent me a couple of questions from HC Verma or something. I'm not mistaken. Just go through those. Okay. Third part is having 5,000 joules, is it? Oh, yes, yes, that's correct. Please make a correction. Yes, Ashwin, that is correct. The third part will come 5,000 joules. This is 10 into 10 is 1 minus 2,000 and 5,000 joules. Okay, so I'm just going to discuss some of the homework question doubts next. MT6 questions we need, let's then keep for another day, because today I want to finish the heat and thermodynamics questions doubts. Okay, so I'm starting with a couple of questions from thermal expansion or heat and temperature chapter from HC Verma. Then I'll move on to the module exercise rounds. So this is heat and temperature HC Verma question number 18. So it says that the ratio of the lengths of an iron rod and an aluminum rod for which the difference in length is independent of temperature. So let's say this is our iron rod. Its length is L1. And this is our aluminum rod. Its length is L2. This is at T equal to T naught. So the difference in length is L2 minus L1 at T equal to T naught. So at a new temperature, at T naught plus delta T, the new length of this one will become L1 into 1 plus alpha of iron into delta T. And the length of this one will become L2 into 1 plus alpha of aluminum into delta T. So at this new temperature, the difference in length is L2 prime minus L1 prime. So this should be the same, because difference is temperature independent. We get the relation that this type of question I've done in class also. So you just compare both sides of this equation, you'll realize that this term should be 0. So this term should be 0. So that means L2 by L1 should become alpha of iron divided by alpha of aluminum. The ratio of the length of the aluminum rod to the length of the iron rod should be inverse of the ratio of the coefficient of thermal expansions. Then what will happen is that the difference in length of the two rods will be independent of temperature. It will be the same at all temperatures. Okay, good. So this one is clear. Next, let's pick up this question, the 19th one. So it says the pendulum gives correct time at 20 degrees C, where G is 9.8 meters per second square. So the time period is correct at a temperature of 20 degrees C for G is equal to 9.8 meters per second square. Now, so this correct time period, whatever it is equal to 2 pi under root L naught upon G. And just for reference, let's take this value of G as G naught. Now we are conducting the same experiment at a different place where the value of G is different. So it's probably at a significant height above the Earth's surface, at a significant altitude. So G is reduced to 9.788 meters per second square. Okay. So what should be the temperature so that time period is accurate? Okay. So basically from the temperature, let's try to understand what should be the L. So I want to the same time period to be this. So if you relate these two, you can see that so I want L naught by G naught to be equal to L by G. So L naught by G naught should be equal to L naught into 1 plus alpha of whatever metal the pendulum is made with upon G, where delta T is equal to so is this step clear? Next, what we'll do here is a bit of approximation. So 1 plus alpha into delta T is basically becoming G by G naught. Okay. And that you can see is 9.788 divided by 9.800. So just to make the calculation easy here, you can see that 1 plus alpha delta T can be written as 9.800 minus 0.012. Correct. Yes. So delta T will come out to be a negative quantity. So it is nearly going to be minus of this. Alpha is given to us in the question as 12 into 10 raised to minus 6. So this is 1000. So we need to be at a temperature which is 1000 less, which is quite ridiculous. So either I made some mistake in calculation. No, they're not going to come in the exam, but they're pretty easy actually. The questions based on thermometry, they are just based on the principle that Yeah, so 12 into 10 raised by minus 3, okay, na, numerator, divided by alpha, which is given as 12 into 10 raised by minus 6. Just check if I made some order of magnitude mistake. I don't think so. Anyway, by my calculation, this appears to be correct. Just check the calculation itself, Javel. The last step, first part in the numerator, delta G by G, you took it as. Oh, okay, okay. This, okay, okay, understood. So, transfer the value wrongly. Yes, it should be 100 in that. Correct. So this is 0.01. So it's correct now. No? So the temperature should be 100 degrees below because we're getting minus. Okay, now let's come to some of the doubts from H.C. Verma's kinetic theory of gases chapter. So kinetic theory of gases, we're going to do question 34 first. So just go through that question all of you. So it says a glass tube sealed at both ends is 100 centimeter long. It lies horizontally with the middle 10 centimeters containing mercury, and the two ends of the tube contain air at 27 degrees C and at a pressure of 76 centimeters of mercury. 76 centimeters of mercury, you know, is atmospheric temperatures, atmospheric pressure. So you can take that as 10 raised to power 5 pascals for 1 atmosphere. The air column on one side is maintained at 0 and okay, so what we do is initially our closed glass tube, it has a section with mercury inside, which is 10 centimeters long. And both the sides had air at a pressure of 1 atmosphere. And a temperature of 27 degrees C on each side, 300 Kelvin. And the whole thing is 100 centimeters long. So this will be how much more? centimeters, 45 centimeters. So the area of cross section is some A. This is at a volume of 45A, and this is also at a volume of 45. Okay. Now what we are doing is we are changing the temperature of the gas on this side to 0 degrees C, and the other side is maintained at 127 degrees C. So we have to find. So what will happen is the moment we start to cool the gas on this side, its pressure will tend to decrease. Yeah, and we heat the gas on the other side, its pressure will tend to increase. So to compensate, the mercury part will come somewhere here now. So this will change. This will become 45 minus x, let's say. And this becomes 45 plus x. Because now this will be at some new pressure, but at a temperature of 0 degrees C, so that is 273 Kelvin, and at a new volume of 45 minus x into K. Now this side will be at the same pressure, because why it has to be at the same pressure? Because this has to be in equilibrium. So the force that this gas is applying must be balanced by the force that is applying. So F should be equal to P into A. Whereas right now earlier the force was F naught. That was P naught into A. So the pressure is unknown, but it's same on both the sides. The temperature we are maintaining at, how much is it? 127 degrees. That's 400 Kelvin. And the volume is 45 plus x into whatever area. So that's it. Okay. So now what we have to do is we have to relate with equation of state. Okay. So P naught V naught upon T naught is equal to P1 or the other PV1 upon T1, which is equal to the same P into V2 divided by. So within this set of equations, we have two independent equations and we have two unknowns. X is unknown and P is unknown. So we can calculate that. So once equate P naught V naught by T naught with P V1 by T, and then again equate it with P V2 by T2. So people understood how to do this question. Yes, Mana, welcome to 24 also. But so we'll do question 30 next, then come to 24. These are the questions I have received in terms of doubts. So if anybody has a doubt in this concept here, please let me know. This is just equation of state, nothing else is being used here. Okay, so just complete this and then go through question number 30 next. Just complete this question and then next go through question number 30. I'm putting up the diagram and everything on the board. Okay, let's understand. Okay, next up, let's understand question number 30. So what's happening in this is that we have a glass cylinder which is 100 centimeters long and kept vertically like this with an open top. Now somewhere in the glass cylinder there is a piston which I think is massless, right? So this total length is 100 centimeters. And we have frictionless light piston. So it's a smooth massless piston. And atmospheric pressure is equal to 75 centimeters. Okay. This is how we express the pressure in barometric terms. It is height into density into G. So when we take density of mercury, H is usually 76 centimeters for P equal to atmospheric pressure, but here they're given it as 75 centimeters. So slightly less. So maybe this is also at an altitude where this experiment is happening. So anyway, the top is closed by a frictionless light piston. The atmospheric pressure is equal to 75 centimeters. Okay, now mercury is, so what we'll have to assume is that initially the piston is not here. Initially the piston is up here. Okay, so the complete thing. So initially, if you look at the free body diagram of the piston, it's experiencing force from above, which is atmospheric pressure into whatever area. It's experiencing force from below, which is whatever pressure the gas is. Let's say it's at pressure P1, volume 100 centimeters into whatever area, and temperature equal to T naught, that is the outside temperature, because glass is a good conductor of heat. So it acts like a conducting wall. So whatever the outside temperature, same will be the temperature of the gas inside. Now from this you can see that F is equal to F naught because it's a massless piston. So that means the initial pressure of the gas P1 is equal to atmospheric pressure. Okay, now the moment we start pouring mercury slowly, the gas undergoes what type of process? It undergoes a compression. But because we are pouring the mercury slowly, while the compression is happening, there is enough time for heat exchange with the atmospheric air outside. So listen to this carefully, okay? We are pouring the mercury slowly onto the piston. So as the piston is compressing this, what will happen is that so we are pouring mercury here. Okay. And the gas inside, it is compressed now to some new pressure P2, some new volume V2, but a temperature which is equal to T naught. Why? Because again it has conducting walls. Okay, so at this stage what is happening? You can see that from this side the force acting will be equal to atmospheric pressure plus density of mercury into G into X into whatever area. And from this side, the force is P2 into whatever area. So at this stage, P2 is equal to atmospheric pressure plus density of mercury into G into X. So that is equal to 75 plus X into density of mercury into G. This is the final pressure. Okay. So now it's saying what is the maximum height to which mercury can be poured. So the maximum height to which mercury can be poured is a situation when X plus whatever this length is, Y, that becomes the original length, L. Okay. So at maximum possible height of mercury column, X. Okay. What is going to happen is that it's going to look like this. Mercury is ready to overflow now because it's reached the top here. So if this is X now, this Y is equal to L minus X. So it's going to be 100 minus X in centimeters. Okay. So now when we put equation of state, now, you'll see we'll get the relation. So P2 V2 upon T0 should be equal to P0 V0 upon T0 because number of moles is conserved. Okay. So in this case, the final pressure is becoming 75 plus X into density of mercury into G into the final volume is becoming 100 minus X into area. This should be equal to the initial pressure. Now initially you can see that this initial pressure was this much. So this was equal to 75 centimeters into density of mercury into G. Okay. And the initial volume was 100 centimeters into area. So this should be equal to 75 into density of mercury into G into 100 E. So this will give us the relation. So 75 plus X into 100 minus X should become 7500. Now solve this for X. So this will give you the maximum height of the mercury column above the piston. So multiple people have asked me this question, so hope it is clear to all of you. Both 30th and 34th. No, Aman, we don't have to relate with any potential energy concept. We are just relating force and pressure. Okay. Pressure is equal to force per unit area, and pressure in terms of column of liquid is given by density of liquid into G into H. This is the working of something called the mercury barometer. You would have studied, I think, in 9th or something. Okay, so hope this question is clear. Now I'll quickly explain question 24 before we conclude today's session. The same thing, same chapter. Question 24 is like this: that we have a container which has a certain volume. So we have a container in which we have kept oxygen gas or something. Now the container has a volume given to us. It's 1 liter. You know, initially there is oxygen gas filled at a pressure of 1.5 atmospheres. And a temperature of 400 kelvins. Now it says that the jar has a small leak and the atmospheric pressure is 1 into 10 raised power 5 Pascal and the atmospheric temperature, so T naught is 10 raised power 5 Pascal and the atmospheric temperature outside is 300 Kelvin. Now there is a small leakage. So initially we have P1 V naught is equal to N1 RT1, where N1 is the initial number of moles. Initial. Okay. Now, due to leakage, final number of moles becomes N1 minus some delta N. But till when the gas will leak? When the final pressure becomes equal to atmospheric pressure. And by then the final temperatures also become equal to this. But the volume of the gas obviously remains V naught inside the container. So we have P2 V naught is equal to N2R T naught. Okay. So this is telling us that 1.5 atmospheres into 1 liter is equal to N1R into 400. And now this is telling us that 1 into 10 raised power 5 pascals in that 1 liter space is accommodating N2 molecules at a temperature of 300. So from this equation and this equation, we can find the number of moles which have leaked out. So delta N is the number of moles that have leaked out. So multiply with the molar mass and you can get the mass of oxygen gas which has leaked out. Okay, understood this? Manas, is this question clear, beta? Okay, very good. Okay, so we will conclude today's session here. Now, just before concluding, a couple of things I want to discuss. Now, in thermal stress chapter, in thermal expansion chapter, there is also a part about thermal stress, where Young's modulus of elasticity or Bulk's modulus of elasticity is related with the thermal expansion or compression. So leave that out for now because we'll be discussing that in when we discuss properties of matter and elasticity. That's one thing. And in kinetic theory of gases, you will see there is something called Maxwell distribution curve and a formula for most probable speed and also mean speed. So that also we'll be discussing later. Leave that out for the moment. Okay. So just concentrate on revising the lectures we have done in class and the class problems and the homework problems that I've given based on that. And you will not have any difficulty with the heat and thermodynamics portion. This is actually a very easy section of physics. So as long as you're systematic with your preparation and remembering the formula and how to apply them, you should have no difficulty. Unlike mechanics, which is a little bit more tricky. So also for the Sunday's test coming up, make sure you do a proper revision of work energy and related concepts. So that's it for today's session, people. Wish you all the best for the test coming up.